Air conditioners and refrigerators are all modern day devices for cooling things down. But what you might be surprised to know is that the principle on which these things work on, which we normally take for granted, captivates a very important area in science, in the science of thermodynamics. These modern day cooling devices work on the concept of entropy or disorder. Entropy is normally regarded as the measure of disorder, but that's not the actual and the scientific definition. The scientific definition is that entropy is regarded as how evenly energy is distributed in a completely isolated system. So the more you have the entropy, the more evenly energy will be distributed. And the lesser the entropy, so there will be more uneven distribution of energy, thus giving you more energy to do some essential work. There's, however, a second definition also, which states that entropy is the measure of the unknown information about different things. But how does entropy relate to the working of these modern day cooling devices? Well, that is the aim of this video. And I'll also show you the modern day research which is being done by scientists on using magnetism to create refrigerators with much more higher efficiencies than the thing which we use today. So you see, the way how these refrigerators actually work is kind of a lot similar to the way how these things work. Yeah, a water pump. So you see, a water pump basically works on Bernoulli's principle. So basically you have a chamber inside there, and when I pump the air using this pump, something called a low pressure region creates inside that particular chamber, and the atmospheric pressure forces the water to just push and just flow out of this nozzle when I push this button. Now suppose you don't have any water in over here. All you have is just pure air. So now when I compress the air inside that particular chamber using this pump, something called a low entropy system is being created. I am decreasing the entropy within that particular chamber because I'm compressing on it. I'm pumping the air. I'm making the air molecules much more ordered. I'm making the matter within it much more ordered. So the different microstates in which these air molecules can occur is decreasing. Thus it lowers the entropy. And as we know that the lower will be the entropy, the more uneven distribution of energy will be there. And that uneven distribution of energy heats up the chamber within there. But you see, when I push this particular nozzle, so I allow the air to flow in pressure. And when I allow the air to flow in pressure, I create a high entropy state over here. So I'm making the air much more disordered. The air molecules are expanding in the surrounding, they're being much more disordered. Thus it creates a high entropy state over here. And whenever there is a transversal from a low entropy system to a high entropy system, there's absorption of thermal energy, thus giving you a net cooling effect. Because you see, when this particular transversal is happening, so the air molecules are expanding, the air is expanding, it creates a high entropy system since the molecules are much more disordered. So since there's a high entropy system over here, there's more even distribution of energy. And that particular even distribution of energy holds on to the heat which it was produced over here. It holds on to the thermal energy, it absorbs the thermal energy, thus giving you a net cooling effect. And that's how these refrigerators work, these modern cooling devices work on this particular principle. This particular effect is known as the Joule-Thomson effect, named after the two physicists who actually worked a lot upon this effect, J.J. Thomson and Joule. And the only difference between this particular demonstration related to the transversal of entropy from a low entropy to a high entropy state and the one which is done in refrigerators is the type of gas which they use. You see, over here we just use normal air, but in refrigerators they use a different type of gas. Earlier they used to use CFCs, chlorofluorocarbons. Now they use mainly 1,1-difluoroethane and some other types of gases to create that transversal of entropy. These gases have a much lower boiling point due to which this particular transverse in entropy can be of a much higher grade. Thus, we can have much more coolness. The temperature can be brought to a much lower temperature because of these different gases which they use. But you see, this particular effect also has its own pros and cons. First of all, a lot of energy is consumed in the compression of the particular gas, as well as its expansion. Secondly, the gas which is used is kind of toxic and harmful for the entire environment. So it's not environment friendly. And that is why scientists are coming up with a new method of cooling things down, a new method, a new technique of making refrigerators using magnetism, electron angular momentum, and aligning magnetic field lines to produce an effect called magnetocaloric effect, which can make refrigerators of a much more high efficiency than what is being used by most of us nowadays. So what is this magnetocaloric effect? So in order to understand the magnetocaloric effect, we first need to understand unpaired electrons. What are unpaired electrons? So you see, any particular atom of any element has its own atomic structure. It has its nucleus made up of protons and neutrons, and there are electrons revolving around that particular nucleus in different energy orbitals. And there is a rule which states that each particular energy orbital can accommodate a maximum number of 2 electrons within a subshell. And those 2 electrons, according to Pauli's exclusion principle, needs to be of the opposite spin. So if you have an upspin electron, the other electron needs to be of a downspin. And you see, spin is the property of every elementary particle. It's not that the particle is actually spinning, it's that the particle has its own angular momentum. So electrons also have this quantum mechanical spin, and they also have this angular momentum. So if you have in a particular orbital only one electron, so you can say that it has an unpaired electron. That particular atom has an unpaired electron, and that particular single electron with its own angular momentum, when it spins around a particular atomic nuclei, it generates something called a net magnetic dipole moment. And that net magnetic dipole moment creates a net magnetic dipole field within the atom. And this same thing happens with all the other atoms of the same element. But the only thing is that since when this element occurs in nature normally without any external magnetic or electric field, this net magnetic dipole moment cancels out each other. So there is no net magnetic dipole field. There is no net magnetic effect on that particular element. The same thing happens in iron. Iron, cobalt, and nickel all have these unpaired electrons. So they have this net magnetic dipole moment, which aligns in different directions, which points in different directions, and cancels out each other, due to which there is no net magnetic dipole field. But when you place that particular element with unpaired electrons in an external magnetic field, so due to that external magnetic field, all those electrons with their own angular momentum align themselves, align their magnetic dipole moment in the direction of the external magnetic field, generating a net magnetic dipole field. And that's how they become magnetized. That's how iron becomes magnetized when it's placed under an external magnetic field, because those electrons, those unpaired electrons with the net magnetic dipole moment align themselves. So the magnetic dipole moment is being aligned, it's being much more ordered, and it creates a dipole field. And when that happens, something called a low entropy system is being created. Why? Because you see, earlier that particular net magnetic dipole moment was pointing in different directions. So it was much more disordered. It had high entropy. But due to the presence of an external magnetic field, that those particular electrons, the net magnetic dipole moment of those electrons align themselves up. So it becomes much more ordered, creating a low entropy system, becoming much more ordered. And this effect is seen at the highest grade with the one element in the lanthanide series called gadolinium. Gadolinium is the only element in all of the elements within the periodic table which shows this particular effect, this particular alienation of the net magnetic dipole moment in the direction of the magnetic field at the highest grade. So when a low entropy system is being created, so what happens is there's an uneven distribution of energy, and that uneven distribution of energy heats the gadolinium up. So the temperature of the gadolinium increases when it surpasses under a magnetic field. And there's also a water outlet which is attached to the gadolinium, so that the water also heats up and it evaporates, thus taking the thermal energy and providing coolness. But when the gadolinium is removed from the magnetic field, when the magnetic field is turned off or it's removed, so the net magnetic dipole moment again starts pointing in different direction and becomes much more disordered. It increases the entropy, and that increase in entropy produces a much more evenly energy distribution which holds on to the heat, providing a net cooling effect, which adds on to the cooling effect which was provided by the evaporation of the water. And it can bring temperatures to very low degrees, to around minus 100 degrees Celsius. And scientists are also actually working on how to use organic molecules to create this effect, to create this magnetocaloric effect. Because gadolinium is a rare earth element, so it's not much commonly found. So it's kind of rare. That's why scientists are also looking for organic molecules which also undergoes this magnetocaloric effect, which aligns its net magnetic dipole moment, creating those entropy transformations and providing coolness. So I hope you liked this video. I hope you learned something new, how magnetism is revolutionizing the way we see at refrigerators or air conditioners. So thank you, that's for now, and bye.